Okay, so good morning, everyone. So the purpose of this presentation is to bring on the table a discussion level. So the intent is to initiate questions and discussion on this. Maybe I will talk a little bit about myself because I'm bringing some of my experience in there. Usually, I'm a functional safety specialist, which means that I'm working in projects that want to use an operating system into a safety critical system, and talk exactly about what Paul and Philippe were talking this morning, is how you break assumptions, how you make sure that the requirement of the safety function can be implemented with the operating system, and what is the knowledge that the integrator needs to know about the OS in order to verify that it's suitable for the need. So that's my everyday job, and I'm using part of it there. So pretty much I'm going to make a long introduction, and you will be worried about, oh, when is he going to start to talk about hardware? It will come. So this introduction, in fact, I added one slide in there based on what we talked about yesterday, because this is about integration. And the question that with Alessandro we want to bring on the table will be in that context. So I thought it would be a good idea to set the context first in which we want to talk, which is the software integrator. So the guy that will be in charge of picking up Linux and putting it in a safety critical system. So that links to also the discussion we had before. Then with Alessandro, we will look into the Linux kernel itself from that point of view, and finish by the question about the abstraction for the hardware that we wanted to bring on the table to open discussion for. So the software integrator point of view, what does that mean, and how does it, I would say, come into play? So I have simplified a little bit the model, but usually the general ideas that will be there are pretty common. So usually, as we talk about, when you talk about safety, the end system is safe, is the one that needs to be safe, whether it's a car, a train, an airplane, or a medical device. This is where, because this is the one that can harm or kill someone. Usually it's not Linux as a software that can kill someone directly, because it has no arm, no legs, no nothing. So that's the one that really have the grade of safety that is required. And the way it works is usually the vehicle maker typically is going to send a request for proposal to someone that will build an equipment that will be put in the end system. So usually the what I call here the OS, I didn't really enter into detail on whether it's a car maker, whether it's a tier 1 or tier 2, because there are all kinds of configuration that can happen in this. So I try to stay simple on this. So usually the end user is going to make an analysis from what can harm or kill people with that vehicle. A lot of the knowledge is already in the community from that, or on the car community, on the aircraft community, and things like that. And there are even regulation in place that says you need to do this and this for this kind of vehicle. So the end user is making a system design, taking into account the safety aspects, and start to define some safety requirements that will be pushed to each equipment. So one equipment about the braking system, one about the flaps of the aircraft, and things like that. So usually it's going to define this kind of requirement and cascade down to the equipment supplier. So most of the time, the equipment supplier have the details about this. Sometimes you need to ask, but usually that's the way it's supposed to work. From time to time, usually in order to save money, you see another pattern that the end user want to reuse something that already exists. So which means that the equipment supplier builds something for a competitor or another use case, and this is pushed to the end user through usually a safety manual that explains how you can integrate it. So it's more than the safety manual, but here, accordingly, we're talking about safety. That's the one I'm focusing on, but there's much more information given to indicate that, oh, I have this if you want, which you can use this way. And the end user can look at it and usually needs to adapt a little bit his general, I would say, final vehicle design to adapt to that. And here we are in the business world. So usually it's a lot driven by money from that point of view. But that's something to keep in mind, because in the end, that's part of the equation. And as Philip mentioned this morning, for the level 3, right now, the money seems to be a key player to say we do it or we don't. So it's just to put it in perspective. And sometimes you're in between. So it starts by an RFP, say, no, I cannot fulfill your RFP, and I can push you this, and you have an iterative approach. And usually in safety, if you don't have an iterative approach, usually you have an issue that will pop up at some point. So you need to talk. That's important to talk about safety. And like we talk about, show the knowledge on what will be used, show what are the failure conditions that could take place. In an equipment, there could be some failure condition that can be pop up. You don't have to solve everything at the equipment level. So that's where the iteration is. There's a discussion to tell where do we put the mitigation for each of the issues that can possibly pop up. The level that will interest us is the next one. The next one is where we are going to make the link between the Linux community, so the OSS world, and the business world. And so here it's not in the cloud that this will happen. It's just that it's a gray area, just to avoid any misunderstanding. So here the kind of activities that will take place is what I have called the Linux integration. So usually it's a more software and hardware integration things, but the part that I will focus a little bit more is the Linux integration. And there are two key points to take into account is the hardware software integration, because as it was taught sometime, not all components have been validated to a particular architecture. So it means that you need to be aware of it, because that may not be an issue, but you need to be aware of it because there are some action to be taken to verify that it's working on a different architecture than the one that has been pushed to the community, for example. Software integration, it's because you will add some additional component. For example, that could be commercial one as well into Linux. So there are these two levels that will have to take place from this point of view. And yeah, we'll see on the next slide, but usually this is really a gray area because you need to have an agreement between all the stakeholders. They need to really work together. If they don't, there are few chances that at the end it will work on at least on time. That's usually when you see that, oh, this equipment has been delivered with 2 years late or things like that. Typically it's because there was not an upfront agreement. They found the problem as they were coming, and it always delayed the delivery of everything, in particular in safety. So to try to look into this gray area, I try to use the 5W and the H kind of approach with the questions, even if I don't have a question for all of them. So, but I thought that it could be a way to enter into the detail. And let's start by the who. Who is going to do the integration? And that way it starts to be a little bit a gray area because it can be different people. And this is part of also the statement of ELISA that the work we are doing here, this is for someone to take it and do the work that will go to safety certification. So the equipment supplier, who is the one that got the requirement from the vehicle, can be the one to jump on it. Usually it depends whether it has knowledge on how to integrate Linux or not. So if he has a pretty good size Linux maintainers in his, I would say, group, then they can do it themselves, for example, and use what we would provide within ELISA to make the complete integration. The good thing is they have access to all the requirements and they know the equipment they are building. So usually they have a lot of information. Another one is for the equipment, you have a hardware layer. So that means that you will have a hardware supplier when the equipment supplier is not building the hardware himself. So the hardware supplier could be another one, because usually you have a BSP level and driver level for Linux. And so the hardware supplier can also contribute to the hardware part. So it can be a well-suitable guy to do that integration of Linux towards the equipment and towards the safety certification. Another one could be a Linux distribution maker. So someone like Red Hat, Canonical, Wind River, or the people which are more specialists into Linux, but may not be specialists into the kind of equipment that is there. So this is where you start to see the relationship that needs to take care to know exactly what needs to be put on the table in order for the equipment to be validated for safety in the end into the final vehicle. A solution maker, I would say it's someone that do a little bit of hardware and Linux packaging, for example, and do a more complete computing platform, for example, that can be used. So I think that should match, and correct me if you disagree, what Electrobit is providing right now with some of the solution that they put together. That could be this. But close collaboration is mandatory and very early in the project in order to have the match. So to give you an example, if you take in the railway, you have a requirement right now that can be pushed very high. When you have something that is failing, that it could be a power failure in the train is going to stop, except in a tunnel. There's new regulation about this. So in that case, the issue, the fact that the train will stop, is pushed to the complete train level and goes even higher. It goes to the, I would say, the train infrastructure, because you rely on the track mechanism to notify the other train that there's been an issue in order not to bump to it. This is just to illustrate that when there's a known failure that can happen, it could be at equipment level or at train level, but even at equipment level that would stop the train, you need to push that knowledge to upper level to see how you handle the answer. So for example, one answer could be that the train maker would say, no, I don't care. If you have a power failure at your equipment level, you need to have a backup power supply. So that way you don't lose power when you continue to progress. So the decision-making on the potential failure can happen at different levels. So that's why it's all about the knowledge about what can go wrong. And so you can decide with the right stakeholders how to address it. Another example I have on one project, it was for a screen that you have in an aircraft that would display some video showing the ground or some other places that were on the same screen that critical information for the pilot. So you need one or the other not to disturb, meaning the video flow was not safe related, so it should not compromise the important information that the pilot needs to see. And the acquisition of the video and the acquisition of the critical data for the pilot were on the PCI bus. So, and when you got the request, say, oh, I want a PCI bus where you can plug two cards, and you need in the software to discriminate between the two so there is no interference between the video flow and the critical patterns that the pilot should see. And you need to demonstrate that for safety. So you want to mix criticality for doing that. That's not to be complex. So here, when you have all the stakeholders on the table, you can put this in there, say it's not to be tricky to demonstrate that mixed criticality, and it's costly. So as soon as you do mixed criticality, you have an extra cost on the project. And in the room, there was the hardware supplier that was there, say, oh, on the silicon, on the chip, on the processor you have selected, there's two PCI Express controller. So on the board, I can put a second PCI Express, I would say, network. So that way we split the two data flows completely, which can make it easier to demonstrate mixed criticality. So here either between two user level approach, or by using an hypervisor and two operating system. But at least by talking with all the stakeholders, it's easier to really find a solution that could simplify, in the end, the usage of the operating system or the global usage of the computing platform. So usually that's a key point. I would say that in my 25 years of experience of doing that job, that is key. And that goes back to some question that were asked before. Do we need to certify the more than 1 million lines of code of Linux? They say, why do you want to certify 1 million lines of Linux? Maybe you just need to focus on part of it and find a way to not have to care about the other one. So that's part of the discussion that takes place in this area around the world. And sometimes this is forgotten, meaning for the newcomers, they just say, oh, here's the RFP and build the equipment and that's it, and I don't care. That doesn't work in safety. And because you have always that money dimension that come into play, and that's a good argument to trigger discussion as well. The other thing on the slide, I was saying that's the shift between the open source community and the business model. And that comes back to what we talked about yesterday. This is where the WHO is adding the liability. So here, this is where you have that shift that start to introduce the liability on what is being done. And because of liability, that's an insurance. Usually you pay an insurance. So that's why it's happening at that point. And it's good to have it in mind because that's where there are decisions that can be taken in there. The what? So what does the Linux integrator has to do about Linux? So that's the part that still, I would say, need to be tuned up. So usually when you look at the standard and the regulation, you have a pretty good list of what needs to be done. But something that is important, in particular, when the equipment integrator is not going to do the work, he is going to rely on someone else that will give a Linux distribution with the material, the information that is required. And we need to assess the suitability of the Linux against the system functional and safety requirements that we got from the vehicle maker. So that part usually means that the Linux integrator needs to know the safety requirement. And sometimes you need to ask, because when you are designing an equipment or when you are designing a vehicle, usually you have a team when they do the safety assessment that start to think about how it should be designed. And sometimes when they give you requirement to build the equipment or the Linux integration, they give you the view of the integration or the design that should be made without telling you all the requirements. So for example, in aircraft, when you are building the display of the cockpit, there's one safety requirement that cascades down from the aircraft maker, which is that the screen, if you have a micro power outage, needs to reboot in 1 second. So in 1 second, you need to be able to completely reboot your equipment in order to display the critical thing. And not the video streaming I was talking about before. This one can come later. But there are some requirements like that. So sometimes I would say the request you got to integrate the OS is not this. It's something different. So talking with all the stakeholders, it's good to ask, why do you want me to do this? And sometimes when you can go up to the requirement, you can change the mind to change what you expect from the OS to be done. So that's usually something that can be done to simplify the level of work you would have and be able to achieve what you want to do with Linux, I would say in a shorter time frame because you have less things to review and something that will be easier to achieve. So there's all that exercise that needs to take place to really define in the end what you expect Linux to do, what we were talking about, what are the safety requirements you want to allocate to Linux? Do you want to allocate some to Linux or something else? So the example that Paul and Philippe were sharing before, that's the conclusion of the discussion. Let's go there because it matches what I want, the safety requirement I have, and it matches my cost as well. So usually these are all the elements that come into the play. So here, this is where you identify this part, and that's part of the talk that needs to take place. Then when you have this agreement, you also need to fill the potential gap when you have to meet the safety certification objective, which are usually given by the safety standard and safety regulation agencies that cascade down, in fact, from the aircraft or the vehicle maker. The vehicle maker will tell you, you need to comply with this standard. And by the way, the regulator asked me to do this as well. Usually you have a list of additional requirements always that you have to fulfill, and you need to be aware of it. And sometimes when you are the Linux integrator, maybe you are just not aware of it. And you have the surprise later on when you start to present the design that you were thinking and the information about how to use Linux properly or the operating system properly. And they say, no, it doesn't work because of this. Oh, you didn't tell me before. That's typical. So that's pretty much the main activities. I didn't enter the detail, but it's the general idea. You need to assess what the Linux you want to put in there, know the safety requirement and the one that will be allocated to Linux. And you need to estimate the potential gap that you have to fill. I will come back to that. This is where ELISA can help with some preliminary analysis that you can reuse, because that's the part that can define the cost in the end. So this is where it can be interesting. And when you have a good relationship with all the stakeholders, you can split the work. Splitting the work usually means two things. It means that you can go faster on putting the system together, but usually it means that you need to have a well-defined integration framework together. You need to know what the others are doing, because that's typical. For example, when you will initialize Linux as an operating system, there are some activities you may want to do. And when you work with the hardware supplier that could provide the board support package and drivers, for example, you need to know who is doing what, because otherwise, when you will start to validate the integration of the system, and when you go, oh, I have the documentation for this, and not this. And usually, the one doing providing the Linux kernel and the one doing the BSP and the driver say, oh, I was thinking that you were doing it. So that's a typical thing as well. And usually when it happens, you just lose 1 year in the delivery of your system.
The human thing.
Yeah. So it's really important, coming back to the previous slide, to have the talk early in the project and define this integration framework early in the project as well, because it doesn't mean that you will not find something you didn't thought about, but you minimize the risk. And that comes back to what Philippe put in the slide. Here, assessing whether the system is safe requires understanding the system sufficiently. And one team cannot achieve that. That's a group thing. That's really a group discussion in order to do this. The when. I didn't put the when initially because I didn't thought that it would be helpful, but we had a discussion yesterday that was interesting, which means that do we have to follow the standard and the regulation or things like that? In some markets, like for example, the space and the automotive, you don't have the regulator that will impose you something. So usually it's you apply the state of the art, so which is ISO 26162 in automotive, which you are of other standard in space, but you don't really have a regulator that imposes you to do it. So here on the market, which are heavily regulatory, at this point in time, if you want to deploy a system with Linux, I would say in the coming 2 or 3 years, I think you have no choice that you have to comply with the current standard and regulation. And the when will be when you will be done with all the gaps that we talk about for the integration point of view to meet the standard and regulation. If you have more time, or if you want to try a new approach, Then the when, it's difficult to say, in fact, in the end, if it will be usually earlier or later than the first one. On the non-regulated market, I would say for the software part, because here it depends on how long it will take you to convince the safety community and the safety regulator, if applicable. But you can see that if you have one, it will take more time usually. That such new approach brings confidence that safety is achieved. So in particular, that was a lot of good point that for complex system, maybe we need to find a new approach to assess, I would say, the safety of an equipment. In the end, it's really the safety of the vehicle that will be looked at. So if we find a new way to approach how you approach Linux for to have the confidence, I would say, in Linux, it will have to cascade, not cascade, but go up to the vehicle for the vehicle people to agree that, okay, it's an acceptable approach. So in particular, the safety community, for automotive, you have the ISO 26262 Safety Club that have several safety manager that they are presenting on a regular basis. So you can put a presentation in that kind of conference to start to see the discussion in there. If you want to talk in behavionics, usually that's where you have the RTCA, the URK, and the SAE bodies that are there to define the standards. And that's a good place to start to see the information because the regulator usually are there. But at least you need to think about it. That if you have a good idea on a new way to approach for complex system, you need to start to see these guys, because for your approach to be used, you need to have the approval from the vehicle maker and for the regulator or the safety company. So you better start now. And as it was asked yesterday, so this is where academic work can help. Because on the previous standard, there were also some academic work that were the start point of the discussion. So this is where the help of academics can be very, very good in there. Because usually academics are known to present papers, to start to see the information around. So they also have the channel to start to talk about it. But I would say that we need to start now if we don't want to have something in 10 years from now. So that's why I did the when. It's to see in fact in the end how long it will take. We cannot put a number in there yet at that point, but at least we have an idea of what needs to be done. So now the how. So I dropped the why and the where, because I didn't find a question to ask for that. But if you have some question, don't hesitate from that point of view. The how, it's usually how you will achieve what is required. This is where the work of ELISA can really help and contribute from that point of view. And if you started to worry when I will start to talk about hardware, I think you noticed that in the previous slide I talked about the hardware supplier, and I will come to it. So I'm still in the global context. So one of the things to do is to demonstrate truthfulness. So you can notice that I use another ambiguous word than safety. So because I didn't want to use safety, so I find another one, but it's still ambiguous. But this is where you need to build the knowledge. And safety is about confidence. So you bring confidence with what we talked before, with saying that this is what I propose, what Linux is doing. In that particular context of use, you don't have to describe in all cases, because it may take you weeks of explanation to someone to talk about that, and they will be lost. So you need to reduce the context and explain the behavior of Linux in that context, and also give a list of what are the failure conditions and what can go wrong. You don't have to fix it, because as we talked before, in safety system, there's a mechanism that you bring up this failure, and you can find other solutions, I would say, at device level or equipment level or at vehicle level. And you need to let that discussion go, because you would be surprised by the interesting solution that can be found. So fixing this is it's not required in safety system, but you need to know about it. So the first step is, for example, to demonstrate the full truthfulness of the required games capability. Usually, this is something you will have to do in avionics because usually when you have a failure or an unexpected behavior, usually you need to make sure that you have captured all the failure condition because you cannot stop the airplane while it's flying. While you can stop a car, you can stop a train, you can stop in some circumstances a medical device, but for a plane you cannot stop it. So that's why usually in the regulation you find for avionics, usually you don't implement the other one to have a monitoring. So the command mon approach of the industrial market usually are not applied in avionics because you cannot afford to have an expected error that you manage for safety because it may stop the plane in the air.
Just to add that when more autonomous functions will be implemented in car and when we see the cars being more autonomously driven, then it would have the same situation in plane.
It doesn't mean because you can still stop the car and flash the warning.
Not so easy, but
it's not so easy, but it's not as critical as the aircraft. So, but that's a good point. You will have to think about it.
Yeah, and I think that many times when we talk about safety, we forget that there is also a safety critical availability aspect. So it's not always possible to simply stop. We must allow the vehicle to move as much as possible.
And that's a very good point. I will come back to that after talking about the two other ones.
We've got a question or comment from Mina on my group online, which is saying, but for automotive, there's a regulator who's enforcing certain standards to use. Why would we say that there is no regulator enforcing standards?
So the standard are for the resistance of the car, the NCAP kind of regulation. So there's a regulator with some standard,
Yeah.
but I'm not aware of any of anyone imposing to comply with ISO 16162.
Yeah.
That's what I'm
Okay.
talking about.
There are the homologation standards, but they don't go so deep as ISO 26262.
In Chinese market,
Oh, in Chinese market?
they say that.
Okay, so
But no,
Yeah, but I think it's all over the world because for now the driver is still in charge.
Hello, can you hear me?
Yep,
Yeah.
we can hear you now, Mina.
Yes, I'm just saying that in regulation, for the NCAP and even for other standards like FUSA and sort of standards, they're enforcing to use certain design patterns and certain techniques in order to protect your system. And for example, there are some standards which are saying you have to use adaptive auto-drive certain versions of adaptive auto-drive, and these versions could be implementing certain safety standards. So, I'm coming from automotive background. I'm talking about, I don't know as a background. So, for the automotive background, the standards enforce you to use certain platforms and certain software solutions with certain safety standards in some systems specifically.
But as far as I know, it's a choice of the car maker. It's not enforced by a state body.
For some systems like emergency braking, it's not a choice. You cannot just go and make a safety case with emergency braking while you have no clear safety standard applied.
So I think there are cars authorized to drive right now, which they didn't demonstrate that they comply with ISO 26262 for the software or the equipment involved in software, because here we are talking about software. I'm not talking about the other pieces, and you're right that for other parts of the car, mechanical one or thing like that, you may have, I would say, standard to fulfill. Here we are in the particular scope of software, and so compliance to ISO 262 for the automotive market. And as far as I know, there are authorized to run right now, which never demonstrated to anyone this.
Yeah.
And they are authorized to
Okay,
run.
so we've got another,
we can debate about this all day, but as far as my experience, there's nothing like system like ASLD, for example, like emergency braking, would go on the street without having four set requirements for the software as well as the mechanical and the hardware parts. This,
I would agree with. I would agree with you on this, but if you don't put the demonstration on the table, that's not going to prevent the car to be used. So here, the point, and I would agree with you that it would be good that it's really enforced at state level, that you would do that, like it's done for the other markets. And but it's also a liability thing, which means that because there's no state body that is there to verify it and to sign that, yes, this has been approved, the state body doesn't bring his liability in there. Why? For example, the FAA and the EASA in avionics, when they approve an aircraft, they put the liability on the table as well for that. And so with the automotive market, it's the liability of the car maker that will be challenged in court for that. And I agree with you that and that's why the car maker usually ask for this standard to be followed, because when you get in court after an accident, it's easier to show that you have followed the state of the art in terms of safety. And in fact, it's an accident, you cannot do more. But it's solved in court with that point of view, but it's only the liability of the car maker usually. And in some cases, well-known example, the car maker tried to push on the driver the liability.
we've got one more question coming in from online.
thank you.
Thank you.
Thanks for the question.
Can you clarify more about preventing monitoring versus error monitoring?
Yep, I didn't went to that yet.
Okay,
So the first one is to, usually that's the one where we want to really trust the whole Linux we are using, and we are going to put everything in place to show that we understand how it works, and we did the failure mode analysis on it to be able to list what are all the possible failure mode, so we can talk at equipment level and potentially at vehicle level how to handle this, and whether it needs to be fixed by something or whether or not. But here it's usually the complete set of software that goes out. Then if you don't want to take the burden of the demonstration of everything, but as soon as you still know what are the issues, you may want to go to a monitoring approach, which means that the burden to follow the standard is pushed more to the monitoring piece of software, which is much smaller. So here it brings a cost point of view that you can reduce the cost of the proof that your system, your monitoring that it's doing good. But it starts to touch the availability you were talking about. Because here, according that you went down to all the pieces of the software to demonstrate the truthfulness, usually you reduce the potential error that could take place. Well, here you could also minimize the level of effort you will put into analyzing, because you have put a monitoring that will detect that there's an error, so you can go in a safe mode. So you have solved the safety, but not the availability. So if you still do a good job, like you would do to demonstrate the truthfulness, usually the monitoring should not trigger. That was what was mentioned in Paul and Philip's presentation. You should not trigger the safety monitor. But if you do not a good job into analyzing what can go wrong, it will trigger more often than you expect. Question is, will your car stop once a month, once a week, once every 10 minutes? That's the availability. You have solved the safety, but you have an availability issue. And that's why they don't use this in the aircraft, because they cannot have availability issues. So they need to have a solution for the plane to continue to fly from that point of view. And the one in the middle, it's usually you have identified some patterns that can trigger a monitor before the problem occurs. A good example, I'm coming back to my video flow coming to a screen and some data that are critical for the safety. You can monitor how many resources and time that the video processing is taking. And when it going over thresholds, you can see that it will start to impact the safety function. And so the preventing monitoring is to put some pattern to check. So you can, if this happens, you see that, oh, the video is consuming more than it was expected, you can stop it. And so you keep the focus on safety and you prevent a violation of the safe behavior to take place. So this one is, I would say, when the safety monitor is triggered, it doesn't mean that the system will not be available because you have put a countermeasure in place, you have put a mitigation, compared to this one, which is more to detect that you have an issue and you go to safe mode.
But the example you gave is, it is preventing, but it's more like predictive, because you could have also preventing in the sense that it traps invalid action and just does not let it propagate.
You can extend to this as well. So there are several levels of prevention that you can do. I just took an example, but it could be a prevention of making a request that you know the impact. Exactly.
Just giving you a time check, we've got 20 minutes before lunch.
Okay, so I need to. So that's good information. Thank you.
Preventive monitoring.
Yeah. Yeah, at least in all cases, it all goes back to knowing your software and knowing what are the failure conditions. And as we said, you can go to the availability. Now we can switch to Alessandro.
Stop sharing.
I will stop sharing.
Yes.
And see what happens.
No.
Nothing.
Getting worse.
Okay. Yeah, it got worse. Okay.
What's this background next time?
I will stop here because I just want to have the slides. I think
Okay.
So at this point, we need to see the role that kernel had in all of this. Let's start by saying that it is the bridge between your application and the software. It provides APIs and let your software talk with the hardware and safely and efficiently. But it doesn't go straight to the hardware every time. The kernel uses drivers, specific drivers, and framework to handle common tasks across devices. Think of framework as a shared logic, something that sits between hardware details and the software, like an interface and main implementation. Internally, the kernel is monolithic, which means that everything is built into one system based on its configuration. As an example, you may see that some small stub function exists and it just becomes full-fledged function by changing the configuration. This makes the configuration critical. A minimal setup can help to isolate the essential and make the system easy to analyze. So before we dive into the safe topics, is important to understand how much is already going on inside the kernel and where we can draw a line between the community work and the vendor's work. To understand the community responsibility and the vendor responsibility begins, we first need to ask what part of the kernel are always in use, no matter what application or hardware is in play. The ELISA community did a formal investigation on this. We used an extremely minimal program, not even an hello world, which would already involve some hardware to print the hello. So this one just starts and enters in an endless loop. That's it, nothing more. The goal was to keep it as hardware agnostic as possible. But interestingly, even a bare minimum program still triggers part of the kernel that abstracts hardware and use it. And the result, which we'll look later, have some hardware specific elements that shows up. So this gives us a baseline, and even the simplest software can trigger some hardware specific details. So what we are exactly trying to achieve by this investigation? The objective was straightforward: define the minimum Linux kernel feature needed for the execution. Not performance, not bells and whistles, just the essential to get an app up and running. To get there, we started by identifying the core function and subsystem that even the simplest application would rely on. Think of it as figuring out what is truly not negotiable. But here's where things get interesting. Kernel, being monolithic, sometimes brings some extra function. Not because your app asked for them, but simply because they are there. An example would be the security feature. You have some stubs in the normal process that does or does nothing based on the configuration or the necessity to have security. So we have to dig deeper and track dependencies and catch those unexpected calls that can sneak in. That's where the configuration becomes our friend. By tweaking it carefully, we can reduce the noise and focus only on what must be there. In the end, the goal was to produce a minimal kernel configuration and a list of features that any application, no matter what, will going to use. So, how we do this? How we did this? To trace the kernel interaction, we used ftrace. We considered the QEMU option too, but instrumented it was more troublesome and brings more trouble than help, actually. ftrace gave us a better visibility, even if it had some complexity in the kernel itself, but it was worth it. So to reduce the noise, we kept the user space as minimal as possible, and we build extremely small build root user space. And instead of relying on block device that would insert some other hardware dependencies, we passed the file system as an initramfs. This kept dependencies low and things cleaner. For the data collection, we used two tools: the min.c, the smallest C program possible that still interact with the kernel, not printf, not extras, statically linked, and without the crt.o. And then we use also the ftraceit, our custom tool, to trace the function call that min.c made, and also to pin its execution on a given CPU and route all the interrupt on the others. Of course, this approach isn't perfect. Some kernel activities, especially stuff happening during the boot and deep internals, won't show in the trace. And there is also always some noise from the kernel activities. Also, ftrace has this nice option to not trace some function because performance problem. And so we need to fill this gap. We compare the ftrace output with the static view produced by KSNav and figure out what was missing from the ftrace trace. The result was not a complete map, was a complete map of what is essential. And we agreed upon the result after we saw it. So, what did we actually find it? First, the essential, at the very end, the process execution is running around the execv syscall. In Linux, a new process, when a new process starts, it is execv that kick it off. And by the way, it is the only syscall guarantee to be in a new process context. That's why we made it a focus on our investigation. From there, the trace confirmed the interaction with other subsystems, especially memory management, which handles things like address space setup and paging. After all, nothing ran without memory. But things got interesting fast. Even with this super minimal program, we saw more happening than we expected. For example, if the size of the program crosses some boundary, the lazy allocation steps in, and suddenly the kernel is doing more than just managing the memory. And there is also another surprise. The crypto API showed up in all this. Not because we were doing anything crypto related on purpose, but because the stack layout and the padding of this stack, the memory subsystem just crossed the boundary of the random subsystem, and the random number generation brings in this cryptographic function. So what the lesson we learned here? That even a minimal program can cause more things than you think. So where did this effort lead us? In this slide, we show the kernel subsystem that our minimal program link.c used. This table here is the list. Each one of those was either directly or indirectly involved in getting this small program up. Now, before we dive into this list, a quick word about what a subsystem even is important. The Linux kernel doesn't have a clean borders inside it. It is not modular in a strict sense. It is monolithic. And everything connects to everything else, potentially. So to make sense of it, we use the maintainers file, which offers a rough breakdown of the responsibility areas. It is not perfect. It was not even meant to define technical boundaries. It is just a way to assign who maintains what. But for this purpose, it gives a reasonable grouping. And as you see, one of the subsystems in the list is the ARM64 port, clearly an hardware specific area. So despite our goal was to avoid relying on specific hardware feature, something is here. But memory management is unavoidable, and memory handling is tightly tied with the architecture. So even in this most abstract case, we need something that is specific to the platform. In the end, this list gives us a realistic picture of what even the most stripped down application touch in the kernel. This is a foundation for understanding what any application will depend on, no matter how simple it can be, no matter what use case we want to use for it. As I wrap up this session, let's take a step back and look at the big picture. Most of the time, the application interact with the hardware through the kernel abstraction layer. This interface, like file system, memory management, and networking stack, hide the hardware complexity, and this is a good thing. It allows software to stay portable and maintainable, which is another. But underneath those abstractions, there is hardware-specific code, the drivers and the low driver implementation that directly deal with silicon. And this is the key point. Maintaining and validating this code, this hardware-specific code, is not something that the community can realistically take on. We simply don't have the time, resource, or access to proprietary hardware details. So while the community can work on improving framework and abstraction, providing perhaps guideline on how to implement the hardware-specific code, it is the responsibility of the silicon to provide code that is safe for their own hardware. That's where we need to draw the line. Yes.
Okay, I would just say though that we do have cases where the silicon vendor is not the upstream maintainer for their boards.
Yes.
And so we have an ambiguity sometimes in those places.
Well, even if a BSP kicks in, the hardware abstraction layer give us the possibility to arrive till a point, and then if any use case need that specific silicon, this specific hardware, this specific code needs to be safe either. We can provide some guideline on how to make it, but we cannot analyze and
Oh, I agree completely on, we can't analyze, I'm just sort of saying that sometimes there is no vendor to rest with.
no vendor.
No hardware vendor to rest with to make sure that the drivers are accurate.
Well, in the end, it's responsibility of who made the use case
Right,
to choose
which
a
silicon they
vendor that
choose.
provide this thing, because
Yes,
if it is not even downstream, it is not even possible to analyze this thing without, for example, an NDA.
Yeah, but I think, I mean, there are two aspects here. One aspect is the systematic capability of the driver itself. For example, if you outsource the driver development and maintainership to Linaro, for example.
yeah, funny
For
that, yeah.
example.
Mhm.
You know, and, you know, there is some, you know, safety aspects to be considered for the reliability of the code, then it will be Linaro that must, you know, upstream the code and the associated tests and whatever, right? But then when it comes to the software hardware interface documentation, so to the hardware programming manual, that is responsibility of the silicon vendor, because Linaro does not own the hardware manual. And I think, you know, if there are safety implications, there should be a sort of DIA, a developer interface agreement between, you know, between, you know, the entity that is developing and maintaining the driver and the silicon vendor itself. So it's a complex, it's not, I would say it's a complex matter. It's not, you know, as simple as saying, you know, safety responsibility for drivers and silicon should rest with vendors.
Yes, but in any case,
Mhm. Great.
what is the response here? The debate is on what ELISA community can do on all this. And I don't think that the ELISA community should go after the framework or hardware abstraction layer boundary,
No,
because
but maybe we could suggest how
Mm.
they could make life easier for us. I think there's a question over there.
I think your point is a very interesting one. If you integrate a driver, which has a safety intent, how do you review the driver? How do you audit the driver? We as a community, for example, open source community, in order to understand whether the work is correctly done, you need to have at least a publicly available safety manual
Mhm.
for that particular hardware. And perhaps it's an excellent point to say that it's something to be expected. I'm not sure if it's something that there will do.
From a, I mean, from a community point of view, you cannot. I mean, usually the safety manual of the hardware is not publicly available.
Yeah,
So
exactly.
you cannot assess the driver against the safety manual of the hardware against the specification of the hardware.
Yeah.
So that is not doable. What we can do from a community perspective, we can, for example, define best practices for open source code development and assess the driver against such best practices. So we can say, do we have requirements defined for these drivers? Do we have testing? Is there structural, what is the structural coverage associated with this test? So aspects that are associated with the systematic capability of the code itself, but you cannot make any assessment in terms of, the driver doing the compatibility of the driver with the hardware itself, or the compatibility of the driver with the hardware safety manual. That is not.
which make my point. We should stop at the hardware abstraction layer as
Yes.
Yes,
information that we provide, and then provide some guidelines on how to make what remains.
guidelines
That's all.
on what people should look for, maybe, with their vendors for hardware. In their safety in the safety manuals from the hardware provider.
How to assess the quality of the software.
Mhm.
How many, not a number, but how many tests are needed for any feature,
Yeah. Mhm.
but no more than that.
Some really basic things though, like we've got a hardware abstraction layer. What assumptions is it making about the hardware? What is it expecting the hardware to do? Actually, that information, if it doesn't exist, then we can be pushing for it to exist, because that will make the interface clearer. Meaning to say that the kinds of, if we were able to review it, what we would be looking for.
But with so much code available, which is not hardware dependent, why focusing on the drivers? I mean, when starting looking at everything else?
Because we're not focusing on the drivers per se, but we're trying to just figure out how to categorize them. So, because if you actually look at the actual composition of the Linux kernel, it's mostly drivers. Just saying.
But if you look at the device, at the real device,
Yeah,
there are only few device drivers,
Correct.
which are, and usually they are,
it's a question, what's gotten
proprietary or-
configured, what's gotten configured into your system.
if you look at what goes around, mostly the core of the Linux kernel gets,
And that's exactly what Alessandro's been
yeah.
studying,
But
so.
So you,
we're in line with it.
just for time checking, you were close to the end.
I were about to pass the ball again to Olivier.
And so the remaining 3 slides, in fact, is a summary of the discussion that just started. It is good.
Okay,
So either we do it now, maybe we need 5 minutes or more, or we go for lunch and we do
If
that
you're able to
afterwards.
do it in 5 minutes, we
Yes.
should stop it within, but you should get it in the 5 minutes.
We can give it a try.
okay.
I think I can go quickly to the questions so people can think
Okay.
about it during lunch.
There we go.
Yeah. So we have a good lunch discussion
Yeah,
or
good lunch
something
discussion.
that I share with commercial participants during.
Mhm.
Lunch Q&A.
Okay.
Avevo un like di 1000, magari se vai sul sito.
So what Alessandro has shown, in fact, it raised a little bit more question, but the focus is on the hardware for this slide. So at least we can trigger other discussion. And when you look at the component that were identified for the minimal kernel, you can identify two kinds of hardware support layer that is there. And we may not need to treat, we will have certainly to treat them differently. So one group, I will come back to the hardware resources with the drivers used by the application, but there's another one, which are hardware support layer that supports some of the design elements of the Linux kernel. So one of them is the MMU. If you want to have user space, the design of the management of the user space is based on the MMU. So here they are tied together. So for this one, and it was started to be studied by Gab as well with the safety architecture working group. That's certainly something that needs to remain, I would say, part of what we can look at, because it's part of the design of Linux. For the others, the discussion has started exactly. We will not have access to all documentation. And in fact, that was the reason of the introduction. Now I'm connecting to my previous part, which is the Linux integrator needs to be aware of the gaps and needs to take action. So either by selecting a proper hardware supplier or suppliers, like with the example of Gab with Linaro and the hardware, that's selecting the stakeholders to do the final integration. So the Linux integrator will be responsible to finding the right teams, the right people, the right companies to jump in to provide the right level of information to be able to achieve all the gaps towards the safety certification. So that was really, I'm glad that the discussion started, because that's about it. And here, something we may have to think about is which abstraction layer do we want to take. So I just put some examples which are user level, which may be more inside the kernel or thing like that. Is, do we want to support all of them? Couple of them? I would say a list of them. There was a good example on one of Philip, I would say, presentation about the VRTIO aspect, which is another layer that can be considered as well.
I think right after the MMU, you have the interrupt controller.
Yes, that's a good one as well. At least we need to make the list of the ones which are critical, because they are linked to the design of the kernel. So that's why I separated two groups. And this one is for the second group. So for the drivers that will come from, I would say, the community or the silicon vendors or the hardware vendors. Do we want to force, I would say, anything like that? So I have a set of questions, which is what I will leave you in mind, and we can talk about it, is, shall we limit the user level API to access hardware resources to a certain framework, or open more things? The more we open, the more work we have to do, the more time it will take to get something done. Shall we drive the discussion with silicon hardware vendors and application developers to determine which abstraction layers, so that start to come back a little bit to see where we can focus? Maybe it could be a good place within ELISA to drive the discussion between the different groups, because we have silicon vendors which are part of ELISA. We have user developer as well that can connect, and maybe we can drive the discussion. Shall we leave the device drivers to silicon and hardware suppliers? So that was the point of Alessandro. That's the natural way you can think, but Gab has a good point that sometimes it will not be the case. But for me, it should be the decision of the Linux integrator. Is the one that may select the hardware as well, or at least he can work with the equipment supplier to see which hardware should be taken, and saying that, no, this kind of hardware, we are never going to get the information, so don't go there.
In my opinion, Russia is now, you have the lunch washed over the fakers, but so in my opinion, there is, so what you presented as hardware abstraction layer, it is an already standardized POSIX API. Mostly.
One of them, there are two of them which are. Yeah.
So what happens, I think in practice, such API is already pretty well standardized. And in fact, if you read the POSIX specification, it says on purpose that the behavior of certain APIs are implementation dependent. Implementation, yeah. And I think the point here is to identify in Linux where what is the actual hardware specific interface, because for most of the drivers, there is a generic driver that sits on top of hardware specific drivers that plug into such specific driver into such generic drivers through callbacks. Like for the washtub, there is a washtub device, washtub driver that is the generic one, and then you have the platform specific driver. So I think
that is part of the hardware abstraction layer, in fact.
yes, but this is, I think that is the generic drivers are the actual interface that determine the boundaries between what is hardware agnostic and what is hardware specific. And this is where you know the silicon and hardware suppliers should plug into.
And that's what we can drive, that kind of information.
Yeah, if we can show that actually all drivers conform to that general model, or we can say actually all drivers don't, there are some exceptions to this model, there's some complexities. And that information alone is I agree with Alessandro, that's enough for us to be able to say, we're pointing to it where I guess our knowledge horizon, we can't go beyond this information horizon because we actually don't have access to the hardware.
It sounds like we have a good lunch discussion group already.
I think we
Choose your words wisely, which you want to say. What prevents you from going to lunch? So yes, there's a last statement from
Yes,
Olivier.
the last question, which is, as we are starting to talk there about guidance about drivers, are we starting to go into a Linux integration guide for safety critical system
Yes,
that we can gather all the information that we already have in the current directory? And this one that we're adding, meaning, could that be the outcome of the ELISA work to give that guide document for Linux integration?
yeah. Well, at this point, let's start gathering out there to go over and we're letting people know online if you find it cool, if you're on time.
Nice.
Yeah, emphasis on we're trying to.
Yeah.
Yes.